Swayam Prabha. Digital India. Educated India.
Now we are going to discuss the ninth module of Unit 2 is primes and related congruence equations. So, this is a combined idea of all the topics what so far we covered Unit 2, right. So, it is very interesting and it will be helpful to understand the cryptograph. Now, the objective of the chapter 9 is we are going to introduce the prime numbers and their application to in cryptograph, and we are going to discuss some primality test algorithm and their efficiencies. And next third one is to discuss the factorization algorithm and their application in cryptography, and we are going to describe the Chinese remainder theorem and its application, and to introduce the quadratic congruences, and to introduce a modular exponentiation and logarithmic. Now, asymmetric key cryptography uses primes extensively. The topic of prime is a large part of any book on the number theory. So, this section is discusses only a few concepts in the factor the way for the chapters in the number theoretical aspects. Once referred the number theory by Button and number theory by Telang and Apostle book, then anybody can understand the checking of these ideas in the chapters. So, I took the lot of problem from these books as well as internet. So, the topic discussed in this section are definition, cardinality of primes, checking for primeness, and Euler-Phi function we discussed, Fermat-Little theorem also discussed, Euler theorem and generating primes. So, these problem already discussed, the topic discussed in this section also further we have to do that in terms of the primes. So, the figure 9.1 says the three groups of positive integers, the positive integers divided into number 1, primes and composition. So, prime number is exactly one divisor and primes is exactly two divisors, and composite numbers consist of more than two divisors. And note that the prime is divisible only by itself and 1. So, what is the smallest prime? The smallest prime is 2, which is divisible by 2 and itself, the only even prime number. And next, list the primes smaller than 10. There are 4 primes less than 10 are 2, 3, 5 and 7, and it is interesting to note that the percentage of primes in the range 1 to 10 is only 40%. So, the percentage decreases as the range increases. So, infinite number of primes, there are infinitely many primes, right. So, in number of primes we have discussed already the pi of n is n by log n, which is less than n by log n minus 1.08366. So, this is interesting in the cardinality of primes. Now, we have to continue that as a trivial example. Assume that only the primes are in the set 2, 3, 5, 7, 11, 13, 17. Here P equal to 5,10,510 and P plus 1 is 5,10511. However, 5,10511 can be a product of numbers 19 into 97 into 277. You see, none of these primes were in the original list. Therefore, there are 3 primes greater than 17. Find the number of primes less than 1, 000, 000. The solution approximation gives the range of 72,383 to 78,543. The actual number of prime is 78,498. So, checking for primeness, give a number n. How can we determine if n is a prime? So, the answer is that we need to see if the numbers divisible by all primes less than root n. We know that this method is inefficient, but it is a good start. So, we have a theorem, if n is a composite, then n has a prime divisors less than or equal to root n. So, we have a proof, if n is a composite means product of two numbers n equal to ab. So, a may lies in 1 to n and b may lies in 1 to n, and we cannot have both a greater than root n and b greater than root n. Since this would lead to ab greater than n, therefore, n must have a prime divisor less than or equal to root n. Next question is 97 a prime? The solution of root 97 equal to root of 97 equal to 9, therefore, primes less than 9 are 2, 3, 5 and 7. So, we need to see that if 97 is divisible by any of these numbers, it is not. So, 97 is a prime. So, the floor you have to calculate and then check it out these numbers, and then we can easily check whether it is a prime or not. Is 301 a prime? The floor of root of 301 is 17. So, we need to check 2, 3, 5, 7, 11, 13 and 17. So, the numbers of 2, 3 and 5 do not divide 301, but 7 does, therefore, 301 is not a prime. So, like that we have to check whether the number is a prime or not. So, Eratosthenes says that C of Eratosthenes says that these are all the possibilities of 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11 to 91. We check it out whether the numbers is prime or not. So, you take number 12 does not divide 2 and 11, and then 13 it does not divide, which one it divides and what divides, it does not divide, like that you have to check it out, the sieve method of finding the prime test. So, we have 13 is a prime, 14 is not a prime, 15 is not a prime, 16 is not a prime, and then 18 is not a prime, 20 is not a prime. Like that in the first row, 6 is not a prime, 8 is not a prime, 9 is not a prime, 10 is not a prime. Like that you have to check it out which is prime, which is not prime, using that table, and we can easily calculate that whether it is divisible by 3 or it is divisible by 2 and so on, we can do that. So, this is the technique they initially started with the checking of the primes. And then the Euler phi function is phi of n, which sometimes called Euler's Tottian function, plays a very important role in cryptograph, that checking of phi of 1 equal to 0, phi of phi equal to phi p minus 1 if p is a prime, and multiplicative function is phi of m into n, or phi of m into phi of n if m and n are relatively primes. And we have properties that phi of p power e equal to p power e minus e, p power e minus 1 if p is a prime. Now, we have a statement of the combining together of the above 4 rules to find the values of phi of n. For example, if n can be factored as the product of prime powers, that is n equal to p1 power e1 into p2 power e2 and so on, pk power ek, then we combine the third and fourth rule to find phi of n equal to p1 power e1 minus p1 power e1 minus 1 into p2 power e2 minus p2 into e2 minus 1 and so on, pk in power e power k minus pk into e power k minus 1. So, this way we can express the Tottian function phi of n, then we can write the product of this expression. So, further we can note that it is difficult to finding phi of n depends on the difficulty of finding the factorization of n. So, keep it in mind how phi of n is depends on finding the factorization. Next, what is the value of phi of 13? If 13 is a prime and we have a property that phi of 13 equal to 13 minus 1, which is equal to 12. And what is the value of phi of 10? The solution is we can use the third rule, phi of 10 equal to phi of 2 into phi of 5. So, phi of 2 is a prime and 2 minus 1, therefore 1, and phi of 5 is a prime, 4 minus 1 is 4, therefore 1 into 4 equal to 4, because 2 and 5 are primes. What is the value of phi of 240? 240 is nothing but the product of prime powers 2 power 4 into 3 power 1 into 5 power 1. According to the previously we expressed the theorem of phi of 240 as 2 power 4 into minus 2 cube and 3 power 1 minus 3 power 0 and 5 power 1 minus 5 power 0. So, it becomes what 16 minus 8 and then 3 minus 1 and 5 minus 1. So, for 8 into 2 into 4, which is equal to 8 into 8 is 64. So, 64 is the required answer to the problem. Now, next problem we can say that phi of 49 is phi of 7 into phi of 7, which is equal to 7 minus 1 into 7 minus 1, which is equal to 6 into 6, that is what we have written, equal to 36. No, the third rule applies when m and n are relatively prime. Hence, 49 equal to 7 square, we need to use the formula of the fourth rule, 7 square minus 7 power 1, which is equal to 42. So, this more careful that this theorem is applied like this. So, carefully do that, the properties and condition is most important. So, sometimes where the fallacy occurred. What is the number of elements in integer modulo 14? So, the answer of phi of 14 is phi of 7 into phi of 2. Phi of 7 is 6 and phi of 2 is 1, therefore, it becomes 6. So, the members are what the one possible relatively primes to this 14 is 1, 3, 5, 9, 11 and 13. So, this is totally how much numbers, 6 numbers, yes, exactly it comes. So, it is interesting point that if n is greater than 2, the value of phi of n is even. Next, Fermat-Little theorem, just we saw that proof also, and most important to recollect all these things. A power p minus 1 is identically equal to 1 under modulo p, and we have a second version, that is a power p into a power minus 1 is identically equal to 1, a power p identically equal to 1 by a power minus 1 equal to a power p is identically equal to a. So, this can be expressed the second version. So, either you can write a per p minus 1 is identical to 1 under modulo p, or a per p is identical to a under modulo p. From this we have a result, find the result of 6 power 10 under modulo 11. Now, we have a statement that 6 power 10 under modulo 11 is 1. So, this is the first version of Fermat's little theorem, where p is 11. Find the result of 3 power 12 under modulo 11. Here the exponent 12 and the modulus is 11 are not the same. So, with the substitution this can be solved using Fermat little theorem, that 3 power 12 under modulo 11 can be expressed 3 power 11 into 3 under modulo 11. So, 3 power 11 into modulo 11 into 3 modulo 11. So, 3 power 11 under modulo 11 is 3, and then 3 modulo 11 is also 3. So, 3 into 3 is 9, 9 is comes under the modulo 11, therefore, it is 9. So, the value of this one is 9. So, this way we can find out using the Fermat little theorem. and we can also find out the multiplicative inverse using these ideas that a power minus 1 under modulo p is also equivalent to a power p minus 2 under modulo p. So, the answer to the multiplicative inverse under modulo a prime can be found without using extended Euclidean algorithm. So, a power minus 1 under modulo 17 can be written as 8 power 17 minus 2 under modulo 17. So, which is equal to 8 power 15 under modulo 17. So, 8 power 15 is nothing but 15 under modulo 17. Similarly, we go to the next problem. 5 power minus 1 under modulo 23 is nothing but 5 power 23 minus 2 under modulo 23 equal to 5 power 21 under modulo 23. So, this value is 14 modulo 23. Next, 60 power minus 1 under modulo 101 is equal to 60 power 101 minus 2 under modulo 101 is 60 power 99 under modulo 101. Therefore, which is equal to 32 under modulo 101. And for next example, 22 power minus 1 under modulo 211 is equal to 22 power 211 minus 2 under modulo 211. Therefore, 22 power 209 under modulo 11, which is equal to 48 under modulo 211. For the first version of Euler's theorem, a power totient function of n is identically equal to 1 under modulo n, and second version we can multiply the phi of n into k, right, and then plus 1, which is identically equal to modulo n, and this will be very useful in cryptograph system of the next unit. And then the version of the Euler's theorem is used in the RSA crypto system of the chapter, next chapter. So, find the result of 6 power 24 under modulo 35. So, we have 6 power 24 under modulo 35 is equal to 6 power phi of 35 under modulo 35. So, we can easily find out the value of this one equal to 1. Next example, find the result of 20 power 62 under modulo 77. The solution is if we take k equal to 1 on the second version, we have 20 power 62 modulo 77 can be written as 20 modulo 77 into 20 power phi of 77 plus 1 under modulo 77 under modulo 77, like that, splitted into 2 like that. So, that 20 this value is 20 and this value is also 20 under modulo 17, this 400 and modulo 17 is 15. So, this way we can calculate the values of 20 power 62 under modulo 77. Next we will go into discuss multiplicative inverses. So, Euler theorem can be used to find the multiplicative inverse under modulo a composite, that is a power minus 1 under modulo n is equivalent to a power phi of n minus 1 under modulo n. For example, we have a multiplicative inverse under modulo a composite can be found without using extended algorithm if we know the factorization of the composite. So, we can write 8 power minus 1 under modulo 77 can be written as 8 power phi of 77 minus 1 under modulo 77 according to the theorem, and phi of 77 is nothing but 60 and then minus 1 is 59 under modulo 77. So, 8 power 59 under modulo 77 becomes 29. Now, we can calculate 7 power minus 1 under modulo 15 is 7 power phi of 15 minus 1 under modulo 15, which is equal to 7 power 7 under modulo 15. Therefore, the value of 7 power 7 is 13 under modulo 15. So, go ahead like that, 60 power minus 1 under modulo 187. So, that 60 power phi of 187 minus 1 under modulo 187, 60 power 159 under modulo 187, therefore, 53 under modulo 187. Similarly, we can go for 71 minus 1 under modulo 100, 71 power phi of 100 minus 1 under modulo 100 equal to 71 power 39 under modulo 100. So, the value is 31 under modulo 100. Now, we have to generate the primes. So, generating the primes is based on the Mersenne prime. So, Mersenne primes is nothing but the statement is m suffix p equal to 2 power p minus 1. You start with p equal to 2. So, 2 square minus 1 equal to 3. If you take p equal to 3, 2 cube minus 1 is 7. If you take 5, 2 power 5 minus 1 is 32 minus 1 is 31. So, like that 2 power 7 minus 1 is 127, and m power 11 is 2 power 11 minus 1 is 2047, and then m power 13 is nothing but 2 power 13 minus 1 equal to 8191, and then m power 7 m 17 is 2 power 17 minus 1 is 131071. Therefore, 2047 is not a prime. We can easily understood that the checking of the primes, which one is a primes, which one is a not prime, how the Mersenne primes is generated, this we can understand the general form of the ideas. A number in the form mp equal to 2 power p minus 1 is called the Mersenne number, and it may or may not be a prime. That is what we explained earlier. So, above values we checked that whether it is a prime or not. So, directly we cannot say that it is a prime. And Fermat numbers, Fermat primes is nothing but f suffix n equal to 2 power n plus 1. Let us start with n equal to 0. So, anything power 0 is 1, therefore, 2 power 1 is 2, 2 plus 1 is 3. So, for f naught will come. When n equal to 1, then 2 power 1 plus 1, which is equal to 2 square 4 plus 1, which is equal to 5. So, f1 equal to 5. Similarly, n equal to 2 power 2 is 17 will come. When n equal to 3, 2 power 3, which is equal to 257, and n equal to 4, 2 power 4 equal to this, and n equal to 5 we have, therefore, it is not a prime. Now, we are going to do for primality testing, finding an algorithm to correctly and efficiently test a very large integer, and output or a prime or composite has always been a challenge in number theory, and consequently in cryptography the recent development look very promising. So, the following topics to be discussed: the deterministic algorithm and a probabilistic algorithm and a recommended primality test. So, this is the deterministic algorithm. So, you have to do the divisibility algorithm with the pseudo code for the divisibility test. This is the inbuilt of divisibility test n. If n is a number of tests for primality, if r is 2 while r is less than root n, if r divides n, return to a composite, then r equal to r plus 1, return a prime. So, we have to make a note of this bit operation is a complexity of divisibility test is exponential. Now, we have a problem. Assume n has 200 bits. What is the number of bit operation needed to run the divisibility test algorithm? The solution is the bit operation is a complexity of this algorithm is 2 power nb by 2. This means that the algorithm needs 2 power 100 bit operations. On a computer cable of doing 2 power 30 bit operation per second, the algorithm needs 2 power 70 seconds to do testing forever. The AKS algorithm is order of log nb base 2 whole power 12. Now, for an example, assume n has 200 bits. What is the number of bit operation needed to run the AKS algorithm? So, the algorithm needs only log 200 base 2 of whole power 12. So, this is the value of this expression, and this bit operations we needed, and then computer capable of doing 1 billion bit operation per second. So, the algorithm needs only 40 seconds. For the primality of testing using the Fermat test, so this is a probabilistic algorithm. If n is a prime, then a power n minus 1 is identically equal to 1 under modulo n. So, if n is a prime, then a power n minus 1 is identical to 1 under modulo n. If n is a composite, it is possible that a power n minus 1 is identical to 1 under modulo n. Does the number 561 pass the Fermat test? Now, use base 2. The number passes Fermat test, but it is not a prime because 561 is equal to 33 into 17. Next question, does the number 561 pass the Fermat test? So, use base 2, the 2 power 561 minus 1 equal to 1 under modulo 561. So, the number passes the Fermat test, but it is not a prime because 561 can be expressed the product of two numbers 33 into 17, a product of primes. Now, we are going to do for square root test. If n is a prime, then root n under modulo n may be equal to plus or minus 1. If n is a composite, then root 1 in modulo n is equal to plus or minus 1 and possibly other values. Okay. What are the square roots of 1 under modulo n if n is 7 a prime? So, the only square roots are 1 and minus 1. So, we can see that 1 square is identically equal to 1 under modulo 7, and minus 1 square is also 1 identically equal to 1 under modulo 7. 2 square is 4 under modulo 7 is 4, minus 2 whole square is also 4 under modulo 7 is 4, 3 square is 9, 9 under modulo 7, 9 by 7, the remainder is 2, therefore identically equal to 2, and then we have a minus 3 the whole square under modulo 7 is 2. So, this is the way we can express the modulo of the numbers. Next, we have what are the square roots of 1 and n if n is 7 a prime. The only square roots of 1 and minus 1, we can see that 1 square equal to 1 under modulo 7, 2 square equal to 4 under modulo 7, 3 square is equal to 2 under modulo 7. Similarly, minus 1 square identically equal to 1 under modulo 7, minus 2 the whole square is 4 under modulo 7 is 4, minus 3 the whole square is 9 under modulo 7 is 2. So, we do not have the test 4, 5 and 6 because 4 is identically equal to minus 3 under modulo 7 and 5 is identically equal to minus 2 under modulo 7, 6 is identically equal to minus 1 under modulo 7. So, what are the square roots of 1 under modulo n if n is 8 a composite? So, there are 4 solutions 1, 3, 5 and 7, which is minus 1. We can see 1 square equal to identically 1 under modulo 8. Similarly, minus 1 square identically equal to 1 under modulo 8. 3 square is identically equal to 1 under modulo 8 and 5 square is identically equal to 1 under modulo 8. So, what are the square roots of 1 under modulo n if n equal to 17 a prime? So, there are 2 solutions of 1 and minus 1. If you take 1 square and we have identically equal to 1 under modulo 7, and similarly minus 1 the whole square identically equal to 1 under modulo 17, and then 2 square is identically equal to 4 under modulo 17 and minus 2 square is identically equal to 4 under modulo 17, and 3 square is identically equal to 9 under modulo 17, minus 3 square is identically equal to 9 under modulo 17, 4 square is identically equal to 17 under modulo 17 is 16, 4 square is 16, because it is inside the 17, therefore 16 only will come. Similarly, for minus 4 square, 5 square is 25, 25 divided by 7, the remainder is 8, therefore it becomes identically equal to 8. Similarly, for minus 5 the whole square, and then 6 square is 36 divided by 17, and then remainder is 2. And similarly, minus 6 the whole square, and the remainder is 2. 7 square is 49 under modulo 17 is remainder is 15. The same way, minus 7 the whole square under modulo 17 is 15, and 8 square is 64 and divided by 17, and that means under modulo 17 is 13 remainder. So, this way we can calculate the square root of 1 modulo n if n is 17. So, what are the square roots of 1 under modulo n if n is 22, a composite? Surprisingly, there are only 2 solutions, because 1 square equal to 1 under modulo 2 and minus 1 the whole square equal to 1 under modulo 2, because 22 is a composite.